So we were discussing about density functional theory, and density functional theory, as we have discussed, is a cornerstone of computation and quantum chemistry. Why the density functional theory is so attractive, at least from the philosophical point of view? Because it reduces the dimension. In the Schrodinger equation, if I have to solve the equation, I am dealing with a 3n dimensional problem if I do not include the spin. If I include the spin, it is a 4n dimensional problem. Whereas in the density functional theory, it is always a 3-dimensional problem. So if I can write the energy somehow as a function of density, remember density is the diagonal element of the reduced density matrix, then does not matter how big my system is, the size will actually reduce to a 3-dimensional one. Problem is, as we have seen, one cannot write the system only in terms of density. First of all, the kinetic energy function cannot be written in terms of density. That will be a bigger problem, and this will continue to haunt us throughout the discussion. And the second problem is that to write the exchange part, I need the pair density or two particle reduced density matrix. So for a real life case, the density functional theory as it is cannot be solved. So in the last week towards the end, what we have seen, how one can solve the density functional theory exactly for a model system, that is uniform electron gas. But we have discussed that the uniform electron gas may be a good approximation for the valence electron in the metal. For molecules, that is not a good approximation. And that is the problem with this kind of theories which actually derives using uniform electron gas, that first of all the density gives a wrong asymptotic behavior. Second thing is that it fails to give the cell structure of the atom, and it cannot describe the bonding in molecules. So molecule does not exist. So today we will go into the density functional theory, which is practical, which will be applicable to molecule, and it gives you an easy way to calculate the energy including the electron correlation. However, the problem is that this is an approximate theory, and we will see that how this approximation has to be taken. There is no clear recipe. We have some idea, like we are like the blind people who are trying to touch and feel the elephant and trying to come with a description of the elephant, but there is no unique way how one can actually canonize at a practical density functional theory. So we are going to use the so-called Hohenberg-Kohn theorem and Kohn-Sham approach, but there are many other ways of doing it, but Kohn-Sham approach is the most practical and most widely used. So before we start discussion on the Kohn-Sham, first let us start with the Hohenberg-Kohn theorem, and this is where the practical density functional theory begins, and this is given by two people, Pierre Hohenberg and Walter Kohn. Walter Kohn went on to win a Nobel Prize for his contribution to the DFT, and because of his work DFT has become a practically solvable model, and also it has become very popular with the chemist. Now the first theorem says that ground state energy is a unique functional of the electron density. That means I can write the ground state energy as some kind of a energy functional which depends upon the rho 0, and this rho represents the density function which is itself is a function of r. We know that rho r is actually dependent upon r, so it is also a function. Now this only is an existing theorem. It just says that there is an unique functional of the electron density. Second thing, this is only applicable for the ground state density, that is also for non-degenerate system. Although latter it can be shown that it can be extended to lowest energy state within each irreducible representation of the point group, lowest non-degenerate state. That means it is not only applicable to the ground state. If any of the excited state belongs to the lowest lowest irreducible representation of that group of a point group, then for that excited state also the Hohenberg-Kohn theorem is also valid. For a general excited state, the Hohenberg-Kohn theorem is not valid as it is. But this form of the theorem does not give me a recipe how to get the density, and that's actually will be a problem. For that, I come to the second Hohenberg-Kohn theorem, which says the electron density that minimizes the energy of the overall functional is the true ground state electron density. So this looks like a variation theorem of some sort, like the one we have used in Hartree-Fock or in CI. So if I start with any density, let us say any trial density, it's a good question how we will get that trial density, but let us get some trial density, and then if we try to calculate energy out of that trial density, provided I know how the mapping from density to the scalar energy is, for every trial density the energy will be higher than what you will get from the exact ground state electron density. So, if I somehow calculate the exact ground state electron density, I can put that on the energy functional, and that energy will be always be lower than what we will obtain for any other arbitrary trial density. So, this in short gives you like a variation kind of a formulation which allows you to find a good density. But if I have the trial density, it is not very clear how I can improve the description of the density. Of course, you can go to Schrodinger equation, and we know exactly in the Schrodinger equation how you can improve the description is to either approximate it like a CI, like a linear equation. So, you increase your variation space, where or you can improve the number of perturbation order, or if you are doing couple cluster, you can use the projection and there also increase the projection space. Here the problem is that the density is a 3-dimensional quantity. So, it is not very clear how I can improve the density, whereas there are very little things to vary, at least from the form of the equation. And of course, one can solve the Schrodinger equation and get a better description of the wave function, and hopefully that will translate into the better description of the density. But the whole aim of getting density functional theory is that I want to avoid the solution of the Schrodinger equation. So, that is not the way that I can calculate Schrodinger equation and get the density back from it. Now, question, how can density be used in a variational equation to determine the energy without recourse to the wave function? That is what we are going to do, and the Kohn-Sham theory actually gives us a recipe for doing that. Now, what you do in the Kohn-Sham DFT is that you take a fictitious system of non-interacting electron. Why I call it a fictitious system? Because first of all, if the system has non-interacting electron, then it is not a real atom or molecule. In real atom or molecule, they will always interact. That is why what I am working with now is a fictitious system. Not only that, it is not only a fictitious, ordinary fictitious system, it is such a fictitious system where the ground state electron density of this fictitious system is same density as the real system where the electrons interact. So, let us say I want to solve for water. I need to find out a fictitious system where the electrons are non-interacting, but still its density is same as the density in an interacting water molecule. How to get that fictitious system? That is a very good question. We will see into that. Now, of course, we know certain things about the fictitious system. First thing is that the real and the fictitious system have the same position, because remember, the cusp in the density actually determines the position of the nuclei. So, if the density of the real and the fictitious systems are same everywhere in the space, that essentially means that their position of the nuclei is same, and the atomic number of the nuclei, which is same as the nuclear charge, that we also have seen that is actually related to the gradient of the density. And because the density is same, the charge of the nuclei for the fictitious system will be same as the charge of the nuclei in the interacting system. So, that is what we know. Now, why I am so interested in getting a non-interacting system? Because if a non-interacting Hamiltonian, I can always write the Hamiltonian as a sum of one electron operator. And if I can write the Hamiltonian as a sum, then of course the energy will be the sum of the individual eigenvalues, and the wave function will be product of one electron orbitals. That means I can now write the eigenfunction as a setter determinant of individual one electron eigenfunctions, which will be an orbital because it is an one electron function. And of course, eigenvalues are sum of the one electron eigenvalues. So, to solve the Kohn-Sham theory, first thing I am doing is that I am bringing back the orbital. Now, this will lead us the trouble back of dimension, because each orbital will have xyz coordinate. So, I am again back in the 3n dimensional problem. So, my original dream to have a method which only depends upon density, that is 3-dimensional, is now fallen. So, I have to now work again on the orbital picture, which is 3n dimensional. But we will see that even with this 3n dimensional system, the computational advantages are much more than what you see in a standard electron correlation method, which scales very steeply with respect to system size. So, I still have a bad scaling, but the scaling will be much less than what you see in a wave function based electron correlation method. So, I am bringing back the orbital. Now, what advantage I will get by bringing back the orbital? Now, the total energy of the system, we have seen this form of the equation, and the first one is the nuclear kinetic energy, and now in this case this is non-interacting nuclear kinetic energy. That means this is the kinetic energy of the fictitious system where the electrons are not interacting. Of course, it has the same density as my interacting system, and this can be calculated from the wave function written as the antisymmetric product of the orbitals. You have already seen that we were calculating the kinetic energy term in the Hartree-Fock also, where my wave function was also a determinant generated out of antisymmetric product. Here I will also do the same thing, because I am now dealing with a non-interacting system. So, I can go back to the orbital picture. So, I can write my total wave function as a antisymmetric product of the orbital, and now I can use the same form of the kinetic energy. Second term is the interaction of rho with the nuclei. So, it is electron nuclear attraction. In some of the cases I was writing it ENE but or VNE, they are both same, and this we know it can be written very easily in terms of classical density. Now, the next two terms. The first term is a classical Coulomb interaction with the rho. So, this is how basically the two rhos actually interact with itself. Problem is that it also contains the self interaction term, and whatever else is left for the exact energy. Remember, this form of the E is not any approximate energy, this is the exact energy, and that everything else it's included in this VXC or exchange correlation term. We will see what is there in this exchange correlation term in much more detail just in a short while, but remember that this is the total electronic energy of the system, total electronic energy as it is. The one term I have not added here is nuclear repulsion. This is generally by convention added with the electronic energy. I have not added it, but it is a scalar quantity, you can always add it, it is an additive constant. This will not change my eigen functions, the eigen values will be shifted by that number, the nuclear repulsion energy. Now, if I now go into the specific components, so this is how it will look like. So, there are 1, 2, 3, 4, 5 terms. What is the first term? The first term is the kinetic energy of the non-interacting electron. This we discussed, and this will be written in terms of rho. We are writing in terms of rho, but what we will finally do is that we will write in terms of orbital like the Hartree-Fock theory. The second one is nuclear electron interaction. This can be written in terms of easily in terms of rho. The third term is the classical electron repulsion energy. This is a Coulomb repulsion energy, and this can also be written in terms of rho. Remember, we have discussed that the whole problem started with the fact that my kinetic energy function cannot be written in terms of density only, it has to be written in terms of reduced density matrix. So, now what I am doing is that I am splitting my kinetic energy part into two terms. First of all, the kinetic energy of the non-interacting system, where because I know they have the same density as the interacting one, I can write the kinetic energy just as for the non-interacting system, and then whatever is the difference between this non-interacting energy and exact kinetic energy, that I will add as a delta additive correction. So, this is the correction to the kinetic energy of the interacting system. Although the non-interacting system and the interacting system have the same density, they do not have necessarily same kinetic energy. So, to use kinetic energy of the non-interacting system is just an approximation. So, there is a correction term which need to be added, and of course, the last term is that non-classical correlation, that is it will contain the exchange as well as the correlation which is beyond what is missing in the Hartree-Fock picture. And what we will do here is that we will take this the correction to the kinetic energy functional and the exchange correlation, and I will club them together into a single quantity which will be known as exchange correlation function. So, whatever I do not know, I will put it into that part. Now, I can now express the energy function in an orbital basis set. So, here you see the energy is written in terms of rho and rho only, no density matrix, not one particle reduced density matrix or two particle reduced density matrix, not any pair density. So, this is only written in terms of rho. So, we have told that the kinetic energy will be written in terms of the one electron wave function, and this is how the orbital will look like. The second term is the electron nuclear attraction, and this is also can be written in terms of the what is called is a wave function in terms of basis. And if you see the quantities which are within this bracket, you see they are exactly identical with what you have learned in the Hartree-Fock. So, this is just like Hartree-Fock. Only problem is that this guys, the one electron orbital may not give me the best Slater determinant. In the case of Hartree-Fock, that was a guaranteed that if I make a Slater determinant out of it, this will give me a determinant which will minimizes the energy, which is may not be true in this case, because my energy is not only that, there are additional terms into it. The third term here is this term here is the Coulomb repulsion of the density, and this is also can be done exactly only in terms of density. And then this fourth term is where all the magic of the density functional theory, or I should say black magic, the exchange correlation functional. Now, how to approximate this exchange correlation functional? This form Hohenberg-Kohn theorem says that there is a functional exists which will map the density to the exact energy, but we do not know much details about this functional, we only know certain properties of it. And of course, n here is the number of electrons. Now, for a dense, we know and we have seen in the Hartree-Fock also that for a Slater determinant wave function, I can write the density like this by taking a product of the orbitals up to n occupied. So, whatever number of orbitals if I occupied, if I take a product of them and integrate it over and take a sum, that will give me the density. And this form of the density is exact for a non-interacting system. There is no approximation. Now, what can be a simplest functional? So, the simplest functional possible is called a local spin density approximation, which is called LSDA, or sometimes this S is dropped and that is directly called LDA, and this was first time given by Kohn-Sham as well as von Barth and Hedin. So, this is one of the basic preliminary density functional theory functionals. So, what you do here? So, you take the form of the energy, remember the form of the energy what we have seen in the previous slide. This form of the energy, if you know the exchange correlation function, it is an exact form. If you know the exact exchange correlation function and if you know the rho, you get an exact energy what you will get by the full solution of the Schrodinger equation in full CI in a complete basis. But what you do here in the LSDA, you take an approximate form of it. What you do in the approximate form? You take the kinetic energy as a Kohn-Sham, that is the non-interacting kinetic energy. Electron nuclear attraction, you add this exactly. The Coulomb part of this, the electron-electron repulsion, the classical part you can add directly here, and this is where it is supposed to have the remaining kinetic energy exchange and correlation. And this depends upon only density. See, this exchange correlation term here does not depend upon density matrix or pair density. This only depends upon the density, which is the diagonal element of one particular reduced density matrix, and it has two parts. The first part, which is written as X, this is the exchange energy, and this exchange energy is taken of an uniform electron gas neutralized by uniform positive background charges. Of course, if I put electron, I have to neutralize it for a molecule. So, I will just put an additional charge to make it neutral. So, this is the exchange part, and the correlation part has been found out by fitting to Monte Carlo calculation for a uniform electron gas. So, this is a very standard straightforward form of the functionals, very less unknown parameters. So, there are two only in this case. Now, I got now a form of the exchange correlation function. Of course, this form is not exact. This is not the exchange correlation function which will give me the exact energy. This is just an approximation, and whatever the difficult terms are there, they are contained in the exchange correlation function. So, it contains actually three things. First of all, it contains the quantum mechanical exchange and correlation. So, whatever is beyond classical, the exchange and the correlation is contained in this term. Second thing is contains the correction for the classical self interaction energy, because the Coulomb term, the way we take as a classical approach, it actually gives the interaction between the densities. That means This term has no way to distinguish the electron between the same or the other. That means it will also contain the self interaction, so the interaction of the electron with itself. This is of course fictitious. How can the electron have an interaction with itself? In Hartree-Fock we knew that it is not a problem because that will be exactly cancelled by the exchange. Here there is no such correction available. So, I need to somehow correct it, and that correction will be also put into the exchange correlation part, the exchange correlation function. And the third thing is that the difference in the kinetic energy between the non-interacting system and the real one, that delta T, that also has been pushed into this system. So, whatever is unknown, that has been pushed into this system. And if I can find out the set of orbital that minimizes the energy which is given in the previous slide, I can find out eigenvalue equation. Now, if you see this form of the eigenvalue equation, you will quickly remember that this form you have already seen. Where you have seen? In the Hartree-Fock matrices. So, this is like the Hartree-Fock eigenvalue equation. The form is same. You again see chi, there is a effective one electron operator, there is an epsilon I which is the like an orbital energy. So, this if I would have replaced this by Fock matrix element, you would thought that this is Hartree-Fock equation. Actually, HKSII is actually Kohn-Sham one electron operator, and this is defined like this. Now, if you see the form, if you see the first two terms, they are same as Hartree-Fock. There is no difference. These two terms are additional, and the first term, at least I know this looks like a J integral or a Coulomb integral, what you have seen in the Hartree-Fock, and this is where the exchange correlation functional thing is. Now, what is the difference between a normal Fock operator and this HKS? The HIKS, the Kohn-Sham one electron operator, correspond to a non-interacting system. But the Fock matrix element, remember, I should not use the matrix element up to the time I use basis. So, the elements of the Fock matrix actually, or Fock operator, actually is not non-interacting. So, it actually includes the interaction in an average way because each electron is moving in an average field of other electron. So, it has this expression 1, 2 where you integrate over all the possible coordinates of 2. So, it is not a non-interacting, it is an average interaction picture, whereas this form of the operator, the way it is given, it is actually non-interacting because it only depends upon the density. Now, Vx is a functional derivative, and this is how you should write it. If the form of the energy function is exact, then the orbitals must provide the exact density, which is minimum correspond to the real system. That essentially means that this orbital will lead to a density. Remember, this density is because it is orbital, so it is a non-interacting density. So, it is a density correspond to the non-interacting system, and this density is same as the exact system. So, this actually fulfills our prophecy that if I can get a fictitious system and if I know the exact energy functional, the orbital will definitely give me the exact functional, and then I can calculate the exact energy also. This orbital also forms the Slater determinant wave function for the separable non-interacting Hamiltonian, and this is how the determinant can be written in the, it is just the diagonal element of the determinant. This we have discussed up to times in the Hartree-Fock. So, basically my recipe now will be somehow to construct this HIKS and then diagonalize it. I will get the orbital, I will construct the Slater determinant, and voila, I get everything out of it. So, this is good. Now, how I will actually solve it? So, if I see the first term of the energy functional to compute the kinetic energy of the non-interacting electron, we have seen how it actually looks like. It actually looks like the first term in the Hartree-Fock matrix, which is actually very convenient for us because I can already use the equations I have made or the codes which I have written for the Hartree-Fock. Now, to determine the Ks orbitals, we will use the same approach as the molecular orbital theory. So, express the Kohn-Sham orbital within a set of basis function. So, take linear combination of atomic orbital to generate molecular orbital. So, here also I will generate this orbital as a linear combination of basis function where individual orbital coefficient will be obtained by a solution of a secular equation entirely analogous to that employed in the Hartree-Fock theory. So, the whole solution, instead of solving the analytic equation, will finally become solution of numerical equation where I will expand these orbitals for the non-interacting system as a linear combination of a atomic orbital. Then I will be left with to find out the appropriate combination coefficient. So in a sense this looks like a LCOMO, but remember the orbitals which I use only correspond to a fictitious system which gives me the same density. It has nothing to do with the energy. Whereas in the case of Hartree-Fock orbital, they actually correspond to the determinant which will give me the lowest energy in the single determinant picture. So in the case of Hartree-Fock orbitals, they have a very well defined significance. They corresponds to the determinant which will give me the minimum energy, whereas in the case of Kohn-Sham, they are just been put fictitiously to fit the kinetic energy functional. So they as such does not have any physical significance, all the orbitals. The HOMO and LUMO has some physical significance, we will discuss into that, but as it is, it does not have any physical significance. So what I can do is that I can replace the Fock matrix element by the matrix element of the Kohn-Sham operator. That is what we will do. This is exactly look like the Fock matrix element. The first kinetic energy terms and the nuclear electron attraction term is same, and this electron repulsion term is actually treated into classical Coulomb, and whatever is left went into the exchange correlation term. So this is what we are going to solve about it.